projects. In this video, we are going to explain about the project, which is MaizeNet, a deep learning approach for effective recognition of maize plant leaf diseases. Introduction of the project. Maize, as the most widely produced cereal crop worldwide, plays a pivotal role in ensuring global food security, serving as crucial source for food, feedstock, and energy supply. Despite its high predictional potential, maize faces significant challenges due to various diseases caused by viruses, viroids, fungi, and bacteria. These diseases can lead to an annual loss of 6% to 10%, impacting both food production and economic stability. The traditional approach for identifying maize diseases involves manual inspection by agricultural specialists. However, this method is prone to misinterpretation, resulting in ineffective pesticide treatments, environmental pollution, and increased toxicity to maize crops. Recognizing the limitations of traditional methods, the introduction of digital technologies, including remote sensing, global positioning, and AI, has revolutionized disease monitoring and forecasting. Automated methods based on computer vision and machine learning algorithms are gradually replacing manual inspection, offering rapid and accurate diagnosis. This project introduces MaizeNet, a deep learning based framework specifically designed for the localization and classification of maize diseases in the field images. Built on faster RCNN network architecture, MaizeNet incorporates improved feature extraction and attention mechanisms to enhance its ability to identify and categorize diseases accurately, even in challenging real world conditions. The framework's effectiveness is demonstrated through extensive experimentation on online accessible database. Objective of the project. The objective of the project is to develop a deep learning based approach, which is MaizeNet, specifically designed for the correct localization and classification of various maize crop leaf disorders. This involves the precise identification of disease spots on maize plant leaves and categorizing them into different classes. The goal is to construct various deep learning models for maize leaf disease classification, including GoogleNet, AlexNet, VGG19, ResNet 18, ResNet 34, Efficient B0, ResNet 50, ResNet 101, Inception ResNet V2, etc. For detection, we have implemented YOLO V5, YOLO CBAM, faster RCNN, and SSD for identifying diseases in maize leaves. Addressing the challenges posed by real-world scenarios, including sample distortions such as noise, background clutter, and blurring of leaf regions. The objective is to compare all the models effectively under diverse conditions, reflecting the complexities encountered in actual agricultural settings. The overarching goal is to empower farmers with timely and accurate information about maize plant leaf diseases, aiding in effective disease management. This project aims to benefit agricultural specialists and researchers by providing a user-friendly tool for simplified disease recognition. The broader agricultural community can leverage these advancements to enhance overall productivity and contribute to global food security initiatives. To implement the project, we need software and hardware requirements. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. And the hardware requirements are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. To implement the project, we have designed various steps in the flow of work. The first step is importing the packages. In this step, necessary Python libraries and packages are imported. We have imported NumPy and Pandas for data manipulation, TensorFlow and PyTorch for deep learning, Flask for web development, Matplotlib for visualization. Coming to the next step, which is exploring the dataset. Here we explore maize leaf dataset for classification, RoboFlow for detection, which includes images of maize leaves with corresponding labels indicating the presence of diseases. Here we understand dataset structure, class distribution, and other relevant details. The next step is image processing. Here we implement an image pre-processing pipeline using image data generator class. This involves rescaling the images to bring them into a common scale, applying shear transformations to introduce variations in leaf shapes, zooming the images for diverse perspectives, horizontal flipping to augment the dataset, reshaping the images to ensure consistency in input dimensions. The next step is image processing using torch vision. For the detection task, we have used Torch Vision library to pre-process images specifically tailored for detection models. This involved normalization and transformation to match the input requirements of the selected detection models. The next step is building the model. Here we define the architecture of the deep learning models for both classification and detection. The next step is training the model. Here we train the selected models using pre-processed dataset. This involves feeding the training data through the model, adjusting the model's weights based on the error, and optimizing the model to improve performance. The next step is Flask framework with SQLite for sign up and sign in. Here we set up a Flask web application to create user accounts and handle authentication using SQLite as a database. This provides a secure and controlled environment for user interactions. The next step is user upload image for analysis. Here we allow users to upload images through the web interface for disease analysis. The next step is pre-processing user input. Here we process the user uploaded images using the same pre-processing steps applied to the training. This ensures that the input is consistent with what the model has been trained on. Using the trained model for prediction. We utilize the trained classification and detection models to predict the disease class and detect diseases in the user uploaded images respectively. The last step is displaying the final outcome. Here we display the results of the analysis to the user. This includes showing the predicted disease class and the classification highlighting detected regions for disease in case of detection. Now we will know what are the algorithms used for classification and detection. First, we will know what is classification. Classification is a machine learning task where the goal is to assign predefined labels to the input data based on its features. For example, in image classification, the model learns to categorize images into specific classes, such as recognizing whether an image contains cat or dog. Coming to detection, object detection involves identifying and locating multiple objects within an image or the video, providing both categorization and spatial information. It goes beyond classification by outlining the position of objects with bounding boxes, commonly used in applications like image-based security systems or autonomous vehicles. Distinction between detection and classification is while classification assigns a single label to an entire input, detection identifies and locates multiple objects within the input, offering more detailed spatial information. Both tasks are crucial in computer vision applications, with classification focusing on categorization and detection providing a comprehensive understanding of object presence and position. Now we will know what are the algorithms used in the classification. The first algorithm is GoogleNet. GoogleNet is also called as Inception. GoogleNet introduced the concept of Inception module, which utilizes multiple convolutional layers with different kernel sizes in parallel. This allows the network to capture features at various scales simultaneously. GoogleNet is employed for its efficient use of computational resources and ability to capture both fine and coarse features. It is particularly useful when dealing with objects at different scales in image classification tasks. The next algorithm is AlexNet. It is a pioneering convolutional neural network designed for image classification. It consists of 5 convolutional layers, followed by max pooling layer and 3 fully connected layers. AlexNet gained attention for its success in ImageNet large-scale visual recognition challenge. Its architecture featuring deep convolutional layers provide effective for image classification tasks. The next one is VGG19. VGG19 is part of visual geometry group architecture known for its simplicity. It has 19 layers, including convolutional layers with small size kernels and max pooling layers. VGG19 is chosen for its straightforward architecture, making it easy to understand and implement. It performs well in image classification tasks due to its deep architecture and small convolutional kernels. ResNet 18 and ResNet 34. ResNet is residual network addresses the vanishing gradient problem by introducing skip connections or the residual blocks. ResNet 18 and ResNet 34 have 18 and 34 layers respectively. ResNet architectures are widely used for deep learning tasks due to their ability to train very deep networks. ResNet 18 and ResNet 34 strike a balance between model complexity and computational efficiency. The next algorithm is EfficientNet P0. EfficientNet employs a compound scaling method, a balanced model depth, width, and resolution. It aims to provide better efficiency in terms of accuracy and computational cost. EfficientNet is chosen for its efficiency in balancing model size and accuracy. It is suitable for tasks where Computational resources are limited, making it efficient for image classification. The next algorithm is ResNet 50 and ResNet 101. ResNet 50 and ResNet 101 are deep variants of the ResNet architecture containing 50 and 101 layers respectively. They include more residual blocks for complex feature extraction. These deeper ResNet variants are employed when more intricate feature extraction is required, such as tasks like object detection or segmentation. The next algorithm is Inception ResNet V2. It combines Inception module with ResNet-like skip connections. This architecture aims to capture diverse features efficiently and enables training very deep networks. Inception ResNet V2 is used when a combination of features from both Inception and ResNet is beneficial. It is suitable for image classification tasks that require a high level of feature diversity. The next one is ConvNext. It introduces a grouped convolutional approach, splitting input channels into groups and applying separate convolutional operations. This allows the model to capture complex patterns more effectively. It is chosen for its ability to capture intricate patterns in the data. It is employed when fine-grained feature extraction is crucial, particularly in tasks with complex image patterns. The next algorithm is MaizeNet. MaizeNet is a custom-designed convolutional neural network tailored specifically for the project's task classifying maize leaf diseases. Its architecture is optimized for capturing relevant features in maize leaf images. MaizeNet is uniquely crafted for the project's objectives, leveraging its architecture to efficiently capture and classify maize leaf diseases. For detection, we have used YOLO CBAM. YOLO is you only look once. CBAM is convolutional block attention module. YOLO is an object detection algorithm that divides the input image into a grid and predicts bounding boxes and class probabilities for each grid cell. YOLO CBAM incorporates the channel attention mechanism, which is CBAM, which focuses on important channels in the feature maps for better representation. YOLO CBAM is used in the project for its real-time object detection capabilities. The addition of CBAM enhances model's ability to attend to crucial channels in the feature maps, leading to improved feature representation. This is beneficial for accurate and efficient detection of maize leaf diseases in real-world scenarios. The next algorithm is faster RCNN, which is region-based convolutional neural network. Faster RCNN is a two-stage object detection algorithm. It introduces region proposal network to generate potential bounding boxes, followed by a classifier to predict the class and define the bounding box coordinates. Faster RCNN is employed when the project places a higher priority on accuracy. In the context of maize leaf disease detection, where precise location and classification are critical for effective treatment. Faster RCNN provides a robust solution, albeit with a slightly longer processing time compared to some other approaches. Coming to SSD, which is single shot multi-box detector. SSD is a single shot object detection algorithm that predicts bounding boxes and the class codes directly from multiple feature maps at different scales. It utilizes a set of default bounding boxes with various aspect of ratios to handle objects of different shapes. SSD is chosen when there is a need for good balance between speed and accuracy. In the project, where timely detection of maize leaf diseases is important. As an extension, we have used deep learning techniques, which are other deep learning techniques for classification and YOLO versions for detection to enhance the performance. And also as an extension, we built front-end using Flask framework for user testing with user authentication. We have used accuracy, precision, recall, and FN score to evaluate the classification models. And these are the performance metrics. So here we have comparison graphs for the classification models for all the performance metrics. This is accuracy comparison graph. X-axis represents accuracy score for each algorithm and on Y-axis represents algorithm names. Similarly, we will have for other graphs also. Accuracy measures the overall correctness of the model by calculating the ratio of correctly predicted instances to the total instances. This is precision score comparison graph. It evaluates the accuracy of positive predictions made by the model. It is the ratio of correctly predicted positive instances to the total instances predicted as positive. This is recall score comparison graph. Recall measures the ability of the model to capture all positive instances. It is the ratio of correctly predicted positive instances to the total actual positive instances. This is FN score comparison graph. It is the harmonic mean of precision and recall. It provides a balance between precision and recall. The algorithm which performs well among all these metrics will be used for final prediction for classifying maize leaf diseases. We have used precision recall and map for evaluating detection models. So here we have comparison graphs for the detection models. This is precision score comparison graph. This is recall score and this is map. MAP is mean average precision. It is a popular metric for object detection that considers both precision and recall at different IOU, which is intersection over union thresholds. It averages precision values across different IOU thresholds and computes the mean. The algorithm which performs well among all these metrics will be used for final prediction in detecting maize leaf disease. To execute the project, first we need to open the code folder which contains source code files. This is the code folder of the project and this is the dataset folder in which we have three class labels, and these are the three different folders in which we have three different types of leaf diseases, and we use these datasets for training the algorithms. And this is the static folder. This folder consists of files related to CSS, JavaScript and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in the HTML templates. These are the model files which contain the algorithm information and that will be loaded into the project code during runtime. This is the classification IPYNB file and this is detection IPYNB files. These are the Jupyter Notebook files which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. This is the sign up file. This file is a database file used to store the user information. Now we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we need to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. By this, current directory will change to the code folder's path. Here we need to type the command python space app.py and then click on enter. This will compile app.py file and it will execute Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which will be the local host and the port unless configured differently. This is the local host and this is the port. Now we need to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project, which is displayed in the browser, and this web page is built by using the Flask framework. Here we can see a register link. We need to click on that first and enter all the registration details if we are signing up newly. I have already signed up and I have an account in it, so we'll directly click on sign in. Here we need to provide our credentials to sign in. So I'm giving my username and the password, and now we need to click on sign in. We have signed in successfully and we are redirected to prediction page. Now we will do the classification and detection of maize leaf disease. First, we will do the classification. For that, under prediction, click on classification. Here, we can see a choose file button. We need to click on that for uploading the images. So I'm clicking on choose file button. I'm uploading the first image. Click on open and now click on upload. So here, we got the prediction as northern leaf blight. Here it means that application has detected the disease in maize leaf and the disease is northern leaf blight. Now we will try giving the other image. Click on try again. Click on choose file. I'm selecting the last image. Click on open and now click on upload. Here we got the prediction as northern leaf spot. Here it means that application has detected the disease in maize leaf and the disease is northern leaf spot. Now we will try giving other image. Click on try again. Click on upload. Click on choose file to upload the image. I'm selecting the second image. Now click on open. And now here we can see that image has been loaded. And now click on upload. Here we can see that the application has predicted the disease as gray leaf spot. Now we will do the detection. For that, under prediction, click on detection. Similar to classification, here is also a choose file button for uploading the images. Click on choose file. Now we will select the images from the other folder. So I'm selecting the first image from the detection folder. Click on open and click on upload. Here we can see that application has detected the disease and it has drawn bounding box around the disease, and it has classified the disease as northern leaf blight and it has named it as northern leaf blight, and it has given a probability score for that. Probability score of detection represents the model's confidence level in accurate identifying an object in an image, with higher score indicating greater certainty. Now we will give the other image. Click on back arrow. Click on choose file. Now I'll choose this image, and now we need to click on open, and now we will click on upload. Here we can see that application has detected the disease and drawn a bounding box around it, and it has labeled as gray leaf spot and a probability score. Click on back arrow. Click on logout. Similarly, if you upload images to the system, then the system will detect the disease and it will classify based on the given disease. Conclusion of the project. The project successfully demonstrates the effectiveness of deep learning methods in recognizing and classifying maize leaf diseases. These models showcase high accuracy in disease classification and precise detection, contributing to the field of plant pathology. The integration of Flask framework with SQLite for sign-up and sign-in, coupled with user-friendly web interface for image upload and analysis, enhances accessibility. The application provides a seamless experience for users interested in diagnosing maize leaf diseases, prompting broader adoption. Through the exploration of various deep learning models for both classification and detection, the project compares the performance of models. This comparative analysis helps identifying the most suitable model for accurately classifying diseases and detecting anomalies in the maize leaves. Farmers, agricultural researchers, and specialists are primary beneficiaries of MaizeNet. The tool empowers farmers with timely information for disease management, enabling them to take proactive measures to safeguard crop health. Agricultural researchers benefit from the state-of-the-art framework for studying and understanding maize leaf diseases, contributing to the advancements in crop science and sustainable agriculture.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.